Good morning, students. Mr. Carver here. Today we're going to talk about tangents to the pole. All right, so we're going to start off with a theorem, or how tangents to the pole are defined, and it is as follows. So you might want to pause this, maybe get this in your notes. If f of alpha is equal to 0, and f prime of alpha is not equal to 0, then the line theta equals alpha is tangent to the pole for the graph of r is equal to f of alpha. I'm going to walk you through this and show you where this comes from and show you how to apply it. But before I do that, I need to spend a little time talking about what f prime of alpha, how that differs from dy dx, that is rectangular slope. So let's talk about that first, and then I'll get back to actually working problems which involve finding tangents to the pole. So why don't we make this the warm-up? Why don't we find dy dx for r is equal to cosine of 3 theta. That is, find the expression for rectangular slope for the cosine of 3 theta. You can pause it now, work it, then hit play. I'm going to go on now. So if you recall from a previous lesson video, x is defined as being r cosine theta, and y is equal to r sine of theta. That is the conversion from polar to rectangular, or rectangular to polar. Actually, polar to rectangular. So if I'm looking for dy over dx, I'm really talking about dy d theta over dx d theta, which means I'm going to use these two to come up with that expression. The problem with that, as we had mentioned before, is the fact that these have r's in it, but that's where the curve that you're using comes in. So my x in this case is really x is equal to the cosine of 3 theta times the cosine of theta, and y is equal to the cosine of 3 theta times the sine of theta. And these are the two that you are going to use to determine what the expression for dy dx is. All right, so let's go ahead and work through that. I take dy d theta. I'm just going to derive this thing right here. That goes in the numerator. That is going to be the product rule. So I'll derive the first. That is going to be negative sine of 3 theta times the derivative of the innermost function, which is 3, times the second, as is. I want to add that then to the first as is, times the derivative of the second, which is the cosine of theta. So that is dy d theta. Dx d theta now, I'll take this right here and derive that with respect to theta. Again, the product rule. I derive the first, that is the negative sine of 3 theta times 3, times the second as is. I want to add that then to the first, times the derivative of the second, which is the negative sine of theta. Right, now that is the expression for rectangular slope. So if I take a look at this graph right here, which is a 3-petaled rose, I know that because of my n value here. It's odd, so that's the number of petals. Each petal being 1 unit long. That's your a value out front that you can't see. There are 2 ways to draw a 3-petaled rose that is symmetric to the x-axis. It's symmetric to the x because of the cosine expression there. So again, 2 ways to draw a 3-petaled rose symmetric to the x-axis. One is pointing to the right, horribly drawn, you get the idea. The other is pointing to the left. Again, horribly drawn. So we need to figure out which one of these it is. And again, to do that, what I'm going to do is do a quick r theta table. So if I do an r theta table, I'm going to plug in the one angle that I know will tell me whether it points left or points right, and that is theta equals 0. I take 0 and I plug it into the cosine of 3 theta. That's the cosine of 0. That's positive 1. I put it right there. That means it must be a rose that points to the right. Now I'm going to make 2 units actually equal to 1. So every one of these concentric circles will be 1/2. That means my first petal is going to look something like that. And again, these are 2 pi over 3 apart. And if you look at the labeling of the circle, it's actually 8 spokes apart. So it's 1, 2, 3, 4, 5, 6, 7, 8. My second one is going to go out to here. make it as pedally looking as possible. 1, 2, 3, 4, 5, 6, 7, 8. My last pedal is going to go right there. There's my 3 petaled rows, 1 unit long. And what I just found was dy dx. That is the rectangular slope for this shape. So for instance, say I was looking at the rectangular slope when theta is equal to 0, I would just take 0 and plug it into this expression and evaluate it, and you would most likely get something that's undefined because the rectangular slope at y equals 0, theta equals 0 is something like that. It's tangent to that curve when theta is equal to 0. All right, so rectangular slope is exactly what you've been dealing with since, what, 5th, 6th grade? F prime of theta is something that is different, and that is this. When you look at r equals cosine of 3 theta, really what you're dealing with is f of theta cosine 3 theta. So when I say I'm looking for f prime of theta, I come up with that expression that gives me negative sine of 3 theta times 3. This is actually giving me the rate at which your r changes with respect to the way that theta changes. This right here is really dr d theta. Change in r with respect to theta. Now, if I make an r theta table based on this equation right here, what you can see is as my thetas increase from 0 to pi over 3, my r's steadily decrease from 1 to 0 to negative 1. So as I make my way around the circle, going from 0 all the way up here to pi over 3, my r values are going to start at 1. They're going to go down to 0, and then they're going to steadily decrease to negative 1. That is, when I'm pointing in this direction, I'm actually backing the truck up 1 unit, which puts me right there on the circle. All right, now if I take a look at my r prime theta table, I'll do that here, and I increase from 0 all the way to pi over 3, you can see that these two values in here are going to be negative. That is, every r prime value from 0 again back to, from 0 to pi over 3 is negative except at the very end points where the change in r with respect to theta is 0. So this is showing you that your r values are decreasing as your theta values increase. So dr d theta, or f prime of theta, is the rate at which r is changing with respect to theta, as opposed to rectangular slope, where you're investigating how the y's change with respect to x. Tangents to the pole investigates how r is changing with respect to theta. And I guess I would just add to this picture, just to make sure that you completely understand this, as I then progress from pi over 3 to pi over 2 along the wheel, what you can see is that my r prime, that is the change in r with respect to theta, goes from 0 back to positive. So as I'm tracing this rows here from 2 pi over 3, which puts me right here on this pedal, you can see that my r's start changing to be more positive. They start growing from negative 1 back toward another positive 1. And you can see that if I use my r theta table, if I plug in pi over 2, I actually get 0 here. So my r's first decreased, which is why you have a negative dr d theta, and then they begin to increase, which is why I have a positive r prime. I hope that's clear, and I hope that you see the distinction. All right, so let's get back to tangents in the pole and actually start working this. All right, and as you recall, the two requirements to find a tangent to the pole: first, f of theta must be equal to 0, and secondly, f prime then of theta cannot be equal to 0. So let's first start off by solving the first portion here. Let's take this and actually find the theta values that give you an r value of 0. All right, and by the way, I adjusted it just slightly. Now I'm taking 3 cosine 3 theta, so I've got a length of 3 petaled rows, And I have a picture of it there to the right. So first I divide both sides by 3, and then I'm going to arc cosine 0. That gives me a 3 theta value of pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. You don't need to worry about how many we're looking for. We're looking for a pattern actually in the answers here. And I'm going to divide all of these by 3. And by the way, these angles go on forever and ever in both directions since there are no restrictions for what theta can be. I then take all of those and divide them by 3. So my theta turns out to be, what is that, pi over 6, 3 pi over 6, or pi over 2. I have 5 pi over 6, 7 pi over 6, etc. in both directions. So I start off with pi over 6, 3 pi over 6, 5 pi over 6, and 7 pi over 6. And what you want to do is just start listing these out until you begin to get repeats. And I don't know if you can see this, but pi over 6, this line right here, pi over 2 is this line right here. 5 pi over 6, obviously this line right here. And 7 pi over 6 is this line right here, which is the same as theta equals pi over 6. So I can strike that here. And I'll just go with those 3, pi over 6, pi over 2, 5 pi over 6. Now I need to double check to make sure that this second condition holds, that f prime of theta is not equal to 0. So what I want to do is take these 3 angles here and plug them into my derivative. So my r prime is equal to negative 3 sine of 3 theta times 3, also known as negative 9 times the sine of 3 theta. And what I want to do is evaluate each one of these at these 3 angles here. So I've got f prime of pi over 6. That's sine of pi over 2, that's positive 1 times negative 9. That is not equal to 0. Check. F prime then of pi over 2. Sine of 3 pi over 2 negative, that's positive 9. That is not equal to 0. Also check. F prime then. Let's do 5 pi over 6. That's the sine of 5 pi over 2. Let's see here. That's positive, negative, no, not equal to 0. Check, check, and check. So these are, in fact, tangents to the pole of this graph right here if I limit it from 0 to 2 pi, which is a way I'm going to have you work it on the test. Now, I think the name tangents to the pole makes sense in this case, right? If you start from 0 and you begin to progress all the way up to pi over 3, if I took a look at that r theta table that I had before, what you're doing is you're tracing out this first pedal from here down to here because we had an r value going from positive 3 to negative 3. And you can see that it's tangent to the pole because those blue dots pass through the pole nice and smoothly, no sharp turns. That line right here, pi over 6, is said to be tangent to the pole because just on those 2 leaves right there, it is certainly tangent to the top of that blue curve there that you can see. All right, so that's how you find tangents to the pole. I'm hopeful that the distinction between r prime and dy dx is now more clear to you. The question that you might have is when wouldn't this hold true? So let me give you one quick example. If you're not interested in that, you can go ahead and pause this video or stop the video. And I think that's enough probably to get you through the homework. So I'm going to go on and show you a case where you're going to get an angle that is not in fact a tangent to the pole. Let's try a cardioid. R is equal to 2 plus 2 cosine theta. So if you remember the shortcuts for drawing this, this is in fact a cardioid. If I take 2 plus 2, add them together, I do get 4, and that is going to point in the positive x direction because of that sign right there and that trig function right there. So positive x direction, this is 1, 2, 3, 4. My conjugate axis is 2 up and 2 down. That's this number right here. Up 2 and down 2. It also hits the pole. That's enough to get this thing drawn. So if I look something like this, I know previously I've drawn that more heart-like, but that bottom, that point shape is in fact rounded. And let's start finding tangents to the pole. Remember, there are 2 requirements. The first is that f of theta be equal to 0, and then the second be that f prime, rather, of theta is not equal to 0. So if I start off by solving this, 0 is equal to 2 plus 2 cosine theta. I subtract 2 and divide by 2. That gives me the cosine of theta is equal to -1. It means my theta is equal to pi. Second requirement is that f prime of theta is not equal to 0, so let's do r prime, or f prime of theta. And when I derive that, I'm going to get -2 times the sine of theta. And I got to check theta equals pi, take that and plug that in here. That does, in fact, give me 0. That is not good. And I think from the drawing you can see why. As you work your way around from 0 to pi, I'm going to be tracing out the top part of this shape right here, from 0 to pi. The problem is it's not tangent. It does not pass through the pole. Rather, it goes from a decreasing r immediately to an increasing r and bounces off the pole and starts to trace out the bottom half of that cardioid. That's why it's not a tangent to the pole. A tangent to the pole must pass through the pole smoothly and continue on the other side. This does not do that. There are no tangents to the pole in this example. All right, guys, that should get you through it. I'll be answering questions on this. Best of luck to you. Thanks.